Okay, so I didn't mean for you to solve this actually. My question was, what do you think was the question for which this is the answer? And the point is, this is expressing the volume, right? What kind of a volume? The volume of what, right? So theta goes from 0 to 2 pi, as usual. That means it's something somewhat circular when looked from above. And then r goes from 0 to 3. So the radius is 3, and so this is what the top view looks like here, right? And then the tricky thing is z goes from 0 to 9 minus r squared, right? So you can also think of this as that if you want, right? And so I think you can have already established, hopefully, that this is a upside down cone, not the cone, a bowl, right? It's a circular paraboloid. Right? And so it's 9 here, and then it hits at 3 when x or y is equal to 3 or negative 3. It crosses, and the cross section, the horizontal cross section, is a circle of radius 3, and so this is what you get. And so what the answer I wanted was that this is the volume. So this is the volume of this solid E, which is a circular paraboloid. Okay, now you can also go ahead and calculate this if you want. And the calculation is not too bad. You can fast forward this part if you like, because you probably have already figured out how to do this, right? It's once you integrate with respect to z, remember r stays the same, right? So it just becomes 9 minus r squared, and then you have that extra r here, that you cannot forget. So this is going to be 9r minus r cubed. That's what you're integrating. And so it's not very simple, but it's not too bad. It's 9 over 2 r squared minus 1 over 4 r to the fourth. And you evaluate this from 0 to 3. And so when you do this, you get 3 squared, which is 9. 9 times 9 over 2 is 81 over 2. And 3 to the fourth is also 81. So it's 81 over 4, okay? And so the inside is just 81 over 4, okay? I mean, that's simple. And then you just multiply by 2 pi, and so that will be 81 pi over 2, and that is the volume of this solid E. Okay, so I think cylindrical coordinates should be rather easy, and I don't think you'll have any difficult time figuring out cylindrical coordinate system. All right, so the second half, spherical coordinates, right? And so the most difficult part is to find what the dv is. And so that's why I am creating, or I have provided you with a separate part of this video, 5.5 extra, where you find that through some hard work on what appears to be like the Earth, and look at the globe, and then find out that dv in spherical coordinates turns out to be rho square sine phi d rho d phi d theta, okay? And you should memorize this rhythmically. So you can say rho squared sine phi d rho d phi d theta, rho square sine phi d rho d phi d theta, rho square sine phi d rho d phi d theta. Okay, that's good enough. So that is what dv is, and you will be using that pretty much every time you have triple integrals in spherical coordinates, right? So let's go back to finding the volume of the sphere with radius a. You know the answer already, right? Because Archimedes told you that years ago, centuries ago, millennia ago, and then we just talked about it too. And then maybe your geometry teacher taught you that when you were in the middle school or in your kindergarten or somewhere, depending on which kindergarten you went to. So V is 4/3 pi a cubed, right? Now notice here, this is going to be incredibly easy in spherical coordinate system, because spherical coordinates, believe it or not, was designed to express parts of the sphere, right? So here, this is what happens. Oh, by the way, you should always write down your bounds, okay? So remember, you have theta first, because I go from the outside, right? So theta goes from 0 to 2 pi, okay? After all, we're talking about the entire sphere. And then phi, oh yeah, so phi goes from what to what? So phi is the angle from the positive z-axis. So it goes all the way here, but that's not 2 pi, is it? Okay, the maximum phi can ever get is 180 degrees or pi, okay? And then, of course, rho goes from 0 to, and I'm trying to integrate this from here, and then gets bigger and bigger, all the way to a, right? Because rho goes from 0 to a, and that's how you find the volume of the radius, a sphere. So dv, oh yeah, not dv. So with this, it really is a very simple expression. It's from 0 to 2 pi, 0 to pi, 0 to a, and then the rest is dv, which is rho square sine phi d rho d phi d theta. Just try to show this to your friends or family, and they will be quite impressed. Wow, it looks like you're really, really smart. You know, I mean, like for most people, this is just incomprehensible, right? Okay, but we know how to communicate because we are calculus people. All right, so let's see. You have, well, what are you integrating with respect to? Rho, okay. So this is almost always going to happen because rho square is a part of dv. The first thing you will probably see in any kind of triple integral as you determine or evaluate it is 1/3 rho cube, okay? That's going to appear pretty much every time because you already have rho square and you have to integrate with respect to rho first. Now sine phi will stay as is until the next step, right? And what is that one? Well, that's a cubed over 3. So let's go ahead and write this. A cubed over 3 outside. And then what you will be left with is the integrand sine phi. And then you have d phi d theta. Okay, all right, so this is a cubed over 3, and then you still have the integral from 0 to 2 pi. What's the antiderivative of sine? That's negative cosine of phi going from 0 to pi, and you have d theta. All right, so let's be careful here because you have the negative sign, which you really don't want to have. But what's a cosine of pi? That's -1. So you have negative, -1, right? Minus, then you have negative 0, cosine of 0, which is 1, right? So it turns out to be 1 plus 1 here. It's actually 2, right? All right, so this is a cubed over 3, and then now you have 2, and then of course you have the integral from 0 to 2 pi of d theta, which is just 2 pi. So it's a cubed 3 to 2 pi, which is 4/3 pi a cubed, as expected. Once again, Archimedes was right. Or as Archimedes would have said it, you folks studying calculus, you guys are right because your answers are same as mine. All right, so that's that. All right, and so now let's do something a little more complicated. All right, and so the next thing we look at is this object. We haven't talked about this before. It's the part of the sphere called a nap, sorry, wrong application, NAPPE. Okay, so what is a spherical nap? A spherical nap is sort of like your shaved ice, all right? So you take a portion of this, okay? And so you have this cone, right? But the cone could have a flat, normally when you think of a cone, you think of a flat, top. But this one actually is not flat on the top. And so we are talking about this entire area, including the spherical part on the top here. Right? So this is called a spherical nap. Let's try to find the volume of a spherical nap. Right? So I should probably have stopped my, we should have started a new page, but that's okay. All right, so let's see. This is where, that's the positive z-axis. That's where phi is equal to 0. Okay, let's go ahead and go to phi is equal to pi over 4. And that means it goes in all directions. Okay, so this is just like a cone, with a spherical top, and that is spherical nap. So you can call this a snow cone because that's what it looks like. The technical name is the spherical nap. Let's find the volume of this. Okay, so what is that? Well, again, theta goes from 0 to 2 pi, right? And then you have to ask, what does phi go to and from? Phi goes from 0 to pi over 4. That's what it says. And then do I have my, so I didn't give you the radius or the rho. Let's say the rho is the square root of 2. So from here to here, that's the square root of 2. And of course, because I'm looking for the volume, I want the rho to go from 0 to the square root of 2. All right, now there is a reason I chose square root of 2. Hopefully you'll see why. I didn't want to have number 2. Square root of 2 would make things a little easier in the next part of this. Okay, so you know my, let's see, anything else we need to know? Oh, you could also try to define this, and I think I will do that. Try to find the volume using cylindrical coordinate system. Okay, and if you try with a rectangular coordinate system, I think it becomes too messy and too complicated, right? But we'll try to do that. And by the way, what happens if the top is not spherical but flat? Okay, if you cut this right at this, you know, thing, the z is equal to whatever this line is. Okay, it turns out to be 1. But anyway, if you have a flat top, then that's not a spherical nap. It's going to be a cone. We'll talk about how to find the area. I mean, the volume of that cone with a flat top using spherical coordinates. It's going to be a little more complicated. But for the for the snow cone, the nap, okay, this is not too bad because all of these are constants. Right? So this is from 0 to 2 pi, from 0 to pi over 4, from 0 to square root of 2, rho square sine phi d rho d phi d theta. By the way, if you're looking for the mass of this nap with a various or varying density function, then the density function goes in here. You'll have something to integrate, right? Right now, I'm not really integrating anything because this whole thing is just dv, right? Okay, so let's go ahead and try to find this. 1/3 rho cubed, not surprisingly, will come in here first. Sine phi is still there, and then you have d phi d theta. This part is a constant, okay, because this is very symmetric. And so this is what? It's 2/3 square root of 2. Now, remember, it's the square root of 2 cubed, which is 2 square root of 2, right? And so let's take this and take it outside of that. And what you'll have is sine phi d theta. Okay. And then you keep going, and of course, the antiderivative of sine phi is negative cosine, right? And then you go from 0 to pi over 4, and then you have d theta. Okay, so let's just try to look at this here. What's a cosine of pi over 4? And that's a square root of 2 over 2, right? So you have negative square root of 2 over 2, okay, minus, of course, negative 1. And so you have to be careful here. You know, you have a negative sign. Oh, yeah, I mean, you could have moved the negative sign to the front here if you wanted to, but I chose not to do it. Probably not a good idea. But anyway, so that's what this is. Now, you know that this is also a constant, okay? And so this is what you have. And then the inside is 1 minus the square root of 2 over 2. And then, of course, go ahead and put 2 pi because that's what you get at the end. So this is 4 pi over 3 square root of 2, and then 1 minus the square root of 2 over 2. Okay. Any questions? I guess I can multiply everything by square root of 2 here. I can distribute this, and then of course this will just become -1 here at the end, right? So that is probably the simplest way to describe this answer. Okay, so a similar question here, right? So I'm going to draw a sphere, okay, as before. And then I will go ahead and do this. And I'm going to do the same kind of thing here. It's like a nap, right? So this is where phi is equal to pi over 4. And so you go in all kinds of directions here, right? And so you end up with a spherical nap. This time though, I'm going to cut this right off right here, okay? And so now we're just talking about the cone, right? So the side view, and this is important, by the way, the side view is going to be like this. So what do I have here? The side view is where, so this is pi over 4, okay? And this is rho, which is the square root of 2. Okay, now I think you can now tell why. This is 45 degrees, right? So that means this is 45 degrees. This is 90 degrees. Okay, so now we're talking about a 45, 45, 90 degree isosceles right triangle, right? And hypotenuse is square root of 2. With that in mind, try to figure out. So this is this is the cone E. My solid is the cone with a flat top. All right. With this in mind, find the volume, and let's say you use the spherical coordinates first, right? And then maybe later you can do the cylindrical coordinate, right? But let's try to go ahead, and this is going to be hard. I have to warn you, it's going to be hard. Try to find out how you may write the spherical coordinates to describe or to express the volume of this E, the cone, right? And I'll get you started here. Theta goes from 0 to 2 pi. That part is easy, okay? Of course it's easy. And then, so what else do I need to have? Phi, okay? Well, phi still goes from 0 to pi over 4 as before, okay? So that's not a problem. Rho goes from 0 to what? Okay, now here's the problem, because what happens is it used to be a spherical nap, right? So rho went all the way from 0 to square root of 2, because square root of 2 was how long the rho was in every direction. But now you have to stop right here, okay? So, and then you have to, if you go this way, it stops here. You stop basically whenever you hit this purple line, which is that, okay? And that line is z is equal to what? Well, it's, remember, this is the isosceles right triangle. If this is a square root of 2, guess what? This is 1 and this is 1, all right? So z is actually equal to 1. The length here is 1. So, so at this point where phi is 0, rho stops at 1. Rho stops, well, it's a little longer than 1 here when the angle is this, and then it gets bigger and bigger. So the point is, this is some function of phi, okay? That's what you have to figure out, all right? So when you think you have established a triple integral that expresses the volume of this E, the cone, okay? Come back to that, and that will be our last part of this section, or the video for this section.